Example 6.9, single stage to orbit. A rocket has a total mass of 100,000 kilograms and a burnout mass of 10,000 kilograms, including engines, shell, and payload. The rocket blasts off from Earth and exhausts all its fuel in 4 minutes, burning the fuel at a steady rate with an exhaust velocity of 4,500 meters per second. Part A, if air friction and gravity are neglected, what is the speed of the rocket at burnout? Part B, what thrust does the engine develop at liftoff? Part C, what is the initial acceleration of the rocket if gravity is not neglected? And Part D, estimate the speed at burnout if gravity isn't neglected. So once again, we've got a final mass, or an initial mass of 100,000 kilograms, an initial mass of 10,000 kilograms. It takes 4 minutes for it to take off and to expend all of the fuel, and the fuel is coming out at 4,500 meters per second. Our final velocity, um, without considering friction or gravity, is basically delta V is the velocity of the emission times natural log of mass initial over mass final. And this will come out to be 4,500 times natural log, and the final mass is 10 times the initial mass, so it'll just be natural log of 10. So it's 10,361 meters per second, or 1.04 E5 to three significant figures. The thrust force. Okay, at the beginning, the equation for that, let's just write it as delta P over delta T. Force equals delta P over delta T, and in this case, we've got a delta M times the emission velocity over delta T. So what is the amount of mass that's coming out? We are going 90. We can estimate if it's coming out at a constant rate, it's going goes from 100,000 kilograms to 10,000 kilograms in 4 minutes. So 90,000 kilograms in 4 minutes is 4 minutes times 60 seconds per minute. And we want the V sub E in there to be 4,500 meters per second. And that comes out to be 1,687,500 newtons. Kilogram meters per second divided by seconds is newtons. So 1.68 E6 newtons. Or, I'm terrible at rounding, 1.69 E6 newtons. They want the acceleration of the gravity, or if the acceleration of the rocket if gravity is not neglected. So I'm going to write acceleration equals the sum of forces divided by the mass. The sum of the forces going up is 1.69 E6 newtons going up minus the mass, 100,000 kilograms times 9.8, mass times gravity. That's the weight. And then on the bottom, we will have 100,000 kilograms. So working that out comes out to a mere 7.1 meters per second squared. As an estimate of this, of the final, including gravity, meters per second squared. One way we could calculate it is to assume it continued to accelerate at this rate, um, or we could assume it is accelerating at a greater rate. Goodness. You know what? I think I'm going to find, this was acceleration init. I think I'm going to find acceleration final, which is going to be that same 1.69 E6, but this time, instead of mass gravity being 100,000 times 9.8, I'll make it 10,000 times 9.8. And I could just put like a smaller value of gravity in there because it's going to be a little further from the Earth, and so that would be smaller. But I'm just going to call it 9.8 for now because I figured that's probably what the book did. And then I'm going to divide that by the 10,000 and see what that comes out to be. And it comes out to be 159.2 meters per second squared, which seems a little strange, except it kind of makes sense because the mass lost is 90,000 kilograms in 4 minutes, which is 3,750 kilograms per second. That means the thing goes from 13,750 to 10,000 kilograms in 1 second, like it quarters its mass or something like that. So about 25% of its mass is burnt in fuel. So that kind of makes that 159.2 meters per second squared make a little bit of sense. So let's look then at the average of these two accelerations. And so that would be, and this is the idea I have in mind, that the final velocity, v final, is equal to the average acceleration times the delta t. And I got a horrendous number. I got 19,956 meters per second. And the reason I think this is horrendous is because without accounting for Earth's gravity, we got 10,361. So we should not get a number higher when we have something pulling down. I think the problem that we just ran into is that I'm thinking of acceleration versus time uh, like this, and then calculating the area under that curve to be 19,956. What actually would be the actual curve for acceleration versus time would have probably been something like this. And so the area under that curve is quite a bit less than the area under that curve. So I need to find another method of estimating. So I'm going to cheat and look at the answer, and it says they estimated the speed of the burnout. They found the approximate loss of speed due to gravity. So they calculated 9.8 times the 9.8 meters per second squared times 240 seconds, the time of 4 minutes, and they ended up with negative 2.35 thousand meters per second. So they just took the 10,361 meters per second minus g delta t. So 10,361 minus 9.8 times 4 minutes times 60 seconds per minute, and came up with 8,009 meters per second, 8.01 E3. So I did not think of this equation. It is a it's kind of a simplification of the impulse momentum law. The impulse due to gravity, it would have had the form impulse due to gravity is equal to the force times the delta t, which would have been mass times gravity times delta t, which would have been mass times acceleration of just the acceleration due to gravity. So cancel those out. Acceleration due to gravity equals g times the delta t. Question 6.9. What initial normal force would be exerted on an astronaut of mass m in a rocket traveling vertically upward with an acceleration a? Answer symbolically in terms of the positive quantities m, g, and a. This would have the form acceleration equals the sum of forces divided by the mass. And we would have acceleration equals the normal force acting upward minus his mass times gravity acting downward divided by his mass. And so ma plus mg equals n. Exercise 6.9. A spaceship with mass 50,000 kilograms is traveling 6,000 meters per second relative to a space station. What mass will the ship have after it fires its engines in order to reach a relative speed of 8,000 meters per second traveling in the same direction? Assume an exhaust velocity of 4,500 meters per second. So we've got a mass initial of 50,000 kilograms, V initial and V final of 6,000 and 8,000, an emission velocity of 4,500 meters per second, and we want to know mass final of this spaceship. So we'll use the equation delta V equals V sub E, emission velocity, times the natural log of mass initial over mass final. Plug in some numbers. V final minus V initial is 2,000. I'll go ahead and divide both sides by V sub E divided by 4,500 equals natural log of mass initial over 50,000 over mass final. And now I'm going to take e to the power of both sides. E to the power of 2 over 4.5 equals 50,000 over mass final, or mass final equals 50,000 divided by e to the 2 over 4.5. So that looks like 50,000 divided by e to the power of parentheses 2 divided by 4.5, and I get 32,059 kilograms, which rounds up to 3.21 E4 kilograms.